Hi guys, welcome to today's video on the NCEA Level 3 Redox Chemistry. So this is the last video I will do for this particular internal because this is more directed towards my school, but again it depends on what school you're in, like I mentioned in my previous videos, because different high schools have different interpretation of the standards, and we can design our questions a little bit differently. Now I know for a fact that from my previous school that I worked at, we were emphasizing on the car batteries, the lead acid battery, and if you're a student from my current school, we are more interested in the comparison between electrochemical cells and electrolytic cells. Okay, so this is normally one of our questions, and we ask you to compare them. So this is where you need to link to the because we may give you some examples, and you can't so if you're one of my students or students from my school, you need to listen up. We are interested in obviously the comparison, but you need to link you can't just make generic comments. You have to link everything that we are looking at, like say in this particular table. You need to link all of these to the specific example that we've asked you to do. Okay, but we'll worry about that later. Let's just go through this particular list. Okay, so electrochemical cells, we did that in one of the recordings, and electrolysis, electrolytic cell, we did that in the other recording. So if you're not sure, pause or exit here, go and watch those videos. But electrochemical cells is normally spontaneous because you are generating electricity. Okay, so you are generating electricity. So this is when you have a battery that's discharging, you generate electricity. Whereas electrolytic cell, you have a negative cell potential value, which means you need energy for this reaction to work. It is not a spontaneous reaction. Okay, so just remember, electrochemical cell, you want the positive overall, and electrolytic cells, you want the negative value. Okay, and that's further enhanced here. You don't need energy supply. The battery produces own power, whereas the electrolytic cell, you need electrical energy to start the reaction and to force the electron transfer. So that's actually quite one of the keywords here, is to force the electrons to go, because naturally they don't want to go. Okay, so you have the oxidant and reductant that just not very keen to react, and you have to give them some incentive to go, and you give them electrons, you give them voltage, and you're forcing them to go. Okay, this one not so, I'm personally not so interested in this, because this is more to do with, that's just really easy. One's going from chemical to electrical, one's from electrical to chemicals. I'm not so fussy on that. This one again, not too this is just a high school setup where we put two half cells in separate containers, and whereas the electrolytic cell, we put one cell, everything in a bulk beaker. Okay, now I do want to talk about salt bridge really quick. I don't think I talked about salt bridge in my electrochemical cell, so I'm just gonna label it like this. For example, this is my anode, this is my cathode. And in my examples I used, in this one, my Zn is turning to Zn2 plus for my anode, and for my cathode, my Cu2 plus is turning to Cu2 plus is turning into Cu. Okay, so I have a salt bridge that connects two things together. So what does a salt bridge do? The salt bridge it has two purposes. One's to connect the circuit, and the other one is to balance the charge. So as you can see, if I have my zinc turning to Zn2 plus, this particular combination on my cathode, it is going to become more and more positive. On my anode, it's going to become more and more positive. On my cathode, it's going to become more and more negative. It's not because I'm producing anything negative, it's just that I'm losing positive, hence is going to be more negative. Okay, so if you have the left hand side beaker and the right hand side beaker, one is becoming more positive, one is becoming more negative, that will make the if the charge separation is too high, the electrons simply don't move anymore. Okay, so what that means is that if you use something like KNO3, which is a very cheap, very common salt bridge material, inside this particular salt bridge, you have K plus ions and CO3 minus ions. So if the left hand side is becoming more positive, the NO3 minus ions are going to go, hey, you're really positive, I'll go hang out with you. And the nitrates and the potassium ions are spectator ions. They don't participate in the reaction, they just balance the charges. So that's what the salt bridge does. I mean, it might be worthwhile to mention it, but again, remember to link to the specific question. You don't need a salt bridge for electrolysis because everything is contained in one cell. Next one. Now, this is a big one. Anode is negative, and because electrons are produced, remember, loss of electrons, oxidation. Cathode is positive because that will attract electrons towards it. Whereas in electrolytic cell, the anode is positive and then the cathode is negative. So you can think about it this way. Let me show you the diagram. So how that works, this is a galvanic cell, so that's the electrochemical cell. Just a fancy word for it. So imagine, imagine this is two separate beakers. Okay, so on the left hand side, and what's going to happen is that I kind of explained this in that video, the anode, you are losing electrons. So you're producing electrons and you're losing electrons, and the electrons are going to the cathode. So you can interpret it in two different ways. Is that first of all, the anode is losing electrons, so this particular electrode is rich in electrons. So what does that mean? That means it's going to be negative. It's going to be negatively charged. Or you can think about the other side, that the electrons are flowing. The electrons are flowing into this electrode. Why? Because this electrode must be positive. That means it attracts electrons, and then it undergoes a reduction reaction. And then if you look at the other side, why is this different? You know, if you look at this diagram, one, I just have a have a lamp. The other one, I have a electrical device, you know, a power pack. Why does the charge of the electrode go opposite now? If you look at the electrons, they're still going the same way, but then you need to understand, because the electrolytic cell, it is a non-spontaneous reaction, what you will need is for the power supply. So to first of all, I explained this in quite a bit of detail in my other video, is to supply electrons. So oops, can't spell. This particular part, so the negative terminal of the let's move my stuff away so I can write properly. Oh god, you can't understand this per terminal. That's horrible handwriting. Excuse me. Let me just still getting used to writing on this tablet. Okay, so the negative terminal of the power supply supplies electrons. So the electrons go into this particular electrode, and that makes that electrode negative, because you can think of it as being electron rich because it's receiving the electrons from the power pack. Or the one that people understand more of, you know, I use the example of, like, say if I am Mg2 plus here, what's going to happen is that the Mg2 plus is going to reduce to form Mg, and the cathode is going to attract all of these negative ions. So this is going to, positive ions. So all of these positive ions are going to surround these negative electrode. So that's why we know the cathode is negative, because it attracts cations. So it attracts the positive ions because it is being that particular ion is being reduced. Okay, and vice versa, the anode is undergoing the oxidation reaction. That means normally, you know, for this side I use the example of Cl minus turning to Cl2, and that means, you know, the negative ions are being attracted onto this particular electrode, and that means it is oxidizing, and that makes the charge of the electrode positive. That is a very big difference, one that you really need to go into a bit of detail to explain it, because you have to link to the examples as well and show really good understanding. Okay, so and then the last one is to look at the electron transfer from the electrochemical cell. So the oxidation reactions to lose electrons, and then these electrons go from the anode to the cathode. Okay, and that is a spontaneous reaction. And then for the electrolytic cell, the power supply, the external power supply supplies electrons to the cathode, and then it forces the electrons out of the anode, and that completes the circuit. Okay, but it doesn't matter which one you have. The anode and the cathode, oxidation always occurs at the anode, reduction always occurs at the cathode. Okay, so just make sure that you can do this comparison. I mean, this is more to do with my people at my school. I just want to make that really clear. Don't go to, if you're not from botany and you go into your home school and you go into internal, you're like, wait a minute, this guy on YouTube told me that this is going to be my internal. You know, just apply some common sense. This is, you know, we're in lockdown and I'm trying to do this. I'm trying to help most people as I can, but you know, my main focus, I'm trying to hit two birds with one stone here, but my main focus is for people at my school. So yeah, so that is one of the questions, but just remember, and obviously I'll talk about this more when we come back to lockdown, you know, in person, but for all the botany people that are listening, it is to do, you can't just write generic comments. You can't just memorize this table, go in and write it down, and then go and complain that where's my exons, I don't get exons, because you need to link to the specific species in the examples. So if we ask you to compare, here's the electrochemical cell, here's the electrolytic cell, can you give us some differences between these? You can't just give us the generic comments. You actually have to look at the balanced half equations. You actually have to look at the volt calculation. You know, when we say calculate the E0 cell value, you actually have to calculate them, use a value, and then compare the two while you're using the two examples. Okay, so you're saying, oh, these are two cells, so what are the two things in the two half cells? Okay, and then you say this is one cell, and then you can talk about this uses salt bridge. Why come the other one? How come the other one doesn't use salt bridge? You can talk about the electron transfer. So what is being oxidized? Okay, it is losing electrons, but where is that going to? So these table is really good. It's a really good starting place for all of you guys, especially from my school. But that's just hopefully reinforce this particular topic. And if you are from, like I said, if you are someone from a different school that you're looking at like NiCad battery, you're looking at lead acid batteries, if you look at any one of those are just really straightforward examples of something that that does both electrochemical as well as electrolysis. So you are just looking at what we call a discharge and recharge. So if you have any rechargeable batteries at home, just think about, all right, so if I'm using it, if I plug that into my TV remote and the remote works, that's because the battery inside is doing a spontaneous reaction. It is generating electricity, and that is allowing your TV remote to work. And if you use it for a little while, that means, and then it stop working, that means you have used up all the chemicals and you have produced a lot of the products which cannot turn back to the original form spontaneously. And that is why you need to take off the batteries, put them in a charger, plug them into the wall, and wait a few days, and that's when the electricity is going to force these products to go back to the original form. And then so that's a recharging process. Okay, so discharge is getting rid of so it's releasing electricity spontaneously. Recharge is using electricity to make it go the other way around. So it's actually quite straightforward if your school do those questions. You know, it's more of a it's a simple they have to give you the formula. They can't expect you to remember the formula. I mean, if your teachers ask you to remember that's a bit hard done by. So that's I'm aware of schools that do that. Now I am also aware of schools that do practical. Like say maybe a teacher does a demonstration, you watch them do it, and then you write it down. I mean, that's pretty straightforward as well. You just everything. And that's the whole reason why I started doing YouTube, because the fundamental chemistry doesn't change. We can change how we assess it, but we cannot change how electrochemical cells work, how electrolytic cells work. Okay, so hopefully that's helpful enough. Now, just to summarize this entire topic for for the level 3s that are listening, you need to, doesn't matter what you do, you need to be able to do your half equations, you need to be able to do your full equations, you need to be able to do your oxidation numbers, you need to be able to do the observations, link all observations to the species. Those are non-negotiable. Doesn't matter which school you're at, those are absolute non-negotiables. You need to be able to identify and justify your choice of oxidant and reductant. You need to go back to the electrochemical cells video, use the standard reduction potential value to justify why this particular species is the oxidant, it's and use the values. This one's more positive, this couple is more positive, therefore this means this particular species is a stronger oxidant and the other one is a stronger, you watch that video. You need to be able to do that. Okay, so it doesn't matter how we play around this thing, those are the key points. And just remember the basics, when you're balancing half equations, the steps that I showed you. When you do comparing oxidation numbers, you're not just comparing the oxidation number of let's say MnO4 minus to Mn2 plus. You're not comparing the overall oxidation number, you're comparing the oxidation number of individual elements. Okay, so it just takes tons of practice, and feel free to leave comments, questions in the comment section. I do attend to those quite quickly, and if you're from my school, you know how to reach me. But all the best with this particular internal, especially during this time of the year. If you are at a school that is doing this a little bit later, and you have any questions, feel free to leave in the comments, and I can make more videos to explain certain things in more detail if that is requested by a lot of people. But yeah, hopefully this series has been helpful enough. I might shift my focus to a bit of level 2 and maybe a bit of level 1 for now, but I do aim to do the internals, all the internals by throughout the year. So for level 3 spectroscopy, that will be a little bit later. Okay, so hopefully this has been helpful enough. All the best if you were doing last minute studying this particular internal before your exam. So all the best, stay tuned, and I'll see you guys next time. Bye bye.